Okay. Thank you. So you waited all this time to learn what is a data commons. So what a data commons. Let's see. I'll just give you a definition that is by Robert Grossman from the University of Chicago, who is one of the co-PIs in the NIH Data Commons, where I was also a co-PI, and we worked together on that. And data commons, as he defines it, brings together or collocates data with cloud computing infrastructure and commonly used software services, tools, and applications for managing, analyzing, and sharing data to create an interoperable resource for a research community. This sounds very similar to all the things we're talking about here when we're thinking of the open cloud, the services that can be provided within the data that needs to be available in the cloud, and all the resources that can be scaled. But what are the differences about when I'm thinking about, well, we're talking about a data commons, and rather than just a bunch of services, software tools in the cloud and data, is the important part to make it a commons is the integration, the interoperability about all these pieces to make it a seamless workflow for research, for the research life cycle, for working on data analysis, data processing, data exploration, visualization, anything that you are going to do with the data, having in one side, all the active research, they're available for you, and all the tools that you need for your active research available, from data collection, if you're collecting directly from an instrument, or surveying it, or from sensors, or from any other sources, to cleaning, processing, analyzing, exploring, and visualizing. But then the other important part that we usually miss when we're working on research and just focusing on the research results, right, is all the data management and all the long-term access or archival or preservation that will help us to have the data there when it's needed for whether it is for validating results from the original study, or for reusing it because it's very valuable data that can be reused for accelerating, for new research in the future, right, or for merging with other data sets and so. But to do that correctly, you need to have a set of other services and tools that will facilitate that, like, for example, having global persistent identifiers, metadata that describes the data, that makes it discoverable, so you can that data set exists, and you know how to access it. Some of the standards or data dictionaries or control vocabularies that will help you to understand that this variable here is the same as this variable here, and you could merge, harmonize data sets. The provenance, the versions to understand what data set you used for a specific research result, right? And provide all the access controls that go with that, and data curation and so. So when you're talking about a data commons, it's bringing all these pieces together, the active research, the data management on the cloud with lots of storage and computing resources. Here are a couple of examples of what a data commons can be. Australia has started the Australian Research Data Commons, and in this case is a set of services that work well together to support researchers in the cloud and access to data. For more specific domain-centric data commons, an example is the Genomic Data Commons by NIH. And in this case, they provide all the specific tools that are needed for not only accessing the data, but also exploring that data and merging it with other data sets. So what do we intend to do to be, well, the Harvard Data Commons to be? How it is different to these data commons that I showed you? So first of all, just to clarify, the Harvard Data Commons is as of now just in a proposal phase, and during these years certain pilots to understand what architecture we need, and understanding the use cases that we need to support. So an inter-collaboration among the different units within Harvard, the library, the Harvard IT, the research computing, the Harvard Dataverse, but also multiple schools. The initial schools that are part of it are the medical school, the School of Public Health, and the business school, but the intention is for all the Harvard schools. And everything that I'm talking about for Harvard Data Commons is something that one could apply to another institution. So you could imagine a similar collaboration for another research institution that wants to provide a data commons for their researchers. And what does it bring together? So in this diagram, just putting examples of all the pieces that are all the tools that could be integrated with that data commons. So there might be Jupyter notebooks. We'll hear from Rory about RSpace as electronic lab notebooks used in the lab, right, and to track the data. And so might be researchers using RStudio, researchers using GitHub for the code. And then what we want to do is that bring snapshots of that research into a repository, in this case, the Harvard Dataverse repository, so that we're tracking what's happening during the research cycle, right, or workflow, but not only just by putting a bunch of files in a place and pointing to that, but actually building whether it's within a container or a capsule or so, building some metadata provenance that are added to the data and the code and the workflows that are part of the research, the outputs of the tools that researchers are using, and connecting that to the data. So that's where this interoperability middleware takes a role, right? And it helps to take all these outputs and add value to it so they can be tracked in a way that follows research data management. If you're not familiar with the importance that is now given into research data management in research organizations, institutions, depending on where you're working on or in industry, that might not be a topic, but this is becoming really critical for a lot of universities, or a lot of academic institutions, and is more generally for any research organization, where for one thing, if you want to be compliant with some of the data sharing requirements for funding agencies or from journals that will require to have access to your data when you publish the paper, right? You would want to start from the beginning with a data management that allows you to track all the workflow of your research, the data, the code, and everything else. But we want to make it very easy for researchers. We don't want to have to ask them to have to track all those things as they go along and have to document constantly. And so the idea of this middleware that as part of the data commons is to facilitate with some tools that are already doing that from the outputs of the tools and services they are using. And then this gets deposited into Harvard Dataverse. Those data sets with the code and everything and metadata are still unpublished. They cannot be found by by the users outside the community, but they can be found within the Harvard research community, right? So you can accelerate collaboration by the fact that they have unpublished data sets that you know exist in the next school, in the next department, and so on. You could have started, you could ask for access to them. But that, when I define this within Harvard, you could think of another community that is Harvard and other universities, and so make that data commons larger. So the concepts still apply. So, and this all lives on top of NESI and NERC and MGHPCC as part of this of the open cloud efforts. So some of from the last couple of minutes, the new features that this will bring, or the last minute, the new features will be the idea of a dashboard where you can find these unpublished data sets for the research community, right? And not only the published ones that you can already find now if you go in the Harvard Dataverse repository, but also these ones that are still researchers are doing active research, but you would want, I mean, not only for the research community is a useful tool to have, but also for the institution to know where are the data sets that researchers are using within my university, right? And where they're located, what metadata is associated with it, and what conditions or data agreements or terms apply to them. So the other piece is that is this interoperability middleware that allows you, facilitates adding metadata and provenance to the outputs of the research tools and then facilitate the deposits through the APIs to the repository. And the third new feature is the integration of the repository with multiple trusted remote storages where you could have sensitive data or very large data sets, so that metadata can be found in the repository, but the data you access it in these remote storage agents. And these we plan to leverage some of the work done in RENCI. Today we heard some talk from RENCI at the University of North Carolina, a project called Impact, and as much as possible, the idea is to leverage a lot of the existing tools and technologies for the data commons and build the interoperability, this integration on top. So thank you.
Okay, next we'll have Rory Macneil talking about RSpace.
Thank you. Hi, everyone. Thanks for having me. It's a pleasure to be here, and a particular pleasure to follow Merce. Hello, everyone. Nice to be here. And I was saying it was a particular pleasure to follow Merce and to see my smiling mentor, Phil, in the audience as well. Phil corrected a lot of the mistakes in this talk on Friday on an emergency basis. So today I'm going to talk about RSpace. So what is RSpace? And I realized, like Dataverse, it's not a computational product. So this is slightly a bit different from many of the other talks and for this audience. So what is RSpace? It's an enterprise-scale electronic lab notebook that's designed for use in large research institutions like big universities. What does that mean exactly? Well, you can also think of it as a digital data hub that's used by research groups in the life sciences. It's Google Docs for science with lots of bells and whistles. There's lots of different ways to think about it. And coming back to one of Merce's themes, it's also an active data management tool, which we've then integrated with an archival data management tool, Dataverse. So I'm not sure if a couple of screenshots will help or not, but if you look on the screen, you can see what the kind of documents you can create in RSpace. So at the top, you'll see there's the workspace, that's where you create and manage documents. Then below that, there's the gallery, which is kind of like the hard drive of your computer, and the two integrate together. And on the left, you can see a structured document, so you can create structures in your documents as well as having simple documents. You'll see on the information panel, you can get lots of information about your documents, which is useful for all sorts of reasons. So what makes RSpace distinctive, which I think is one of the reasons that it fits in well with the data commons idea, is it's very flexible, which is suited to academic research environments where things often change. Connectivity, interoperability, which I'm going to talk more about in a moment. And traceability, which is very important in terms of both IP protection, identifying who did what, made what contributions, et cetera. And also it has support for both molecular biology and chemistry, which are the two core disciplines which use products like these. As a company, something which I think distinguishes us is that we very much developed a product through collaborations with our universities, which are our customers, but also our partners. So the product was actually developed in intensive engagement with the University of Wisconsin a number of years ago. And after that, we've continued to work on development with Harvard and other universities. So this is kind of the, this is our story, really. This connected approach, coming back to the interoperability theme, which Merce introduced. So if you look at this on the left, we have several kinds of interoperability. We have interoperability with data and files, interoperability with instruments, interoperability with tools, and interoperability with repositories. So the idea is that many of the other products which approach this problem are in effect silos. But our whole approach, which we really was informed by the University of Wisconsin, was to be part of an ecosystem. So the ecosystem continues to grow because we understand that researchers, when they're working on their, running their experiments and documenting their research, they need to continue to use all of the other resources which they're already using. So this product is not meant to replace the other tools they're using, but to complement and to supplement the other tools they're using. So you can make links from RSpace to things like OneDrive and Google Drive and Box and Dropbox, where you might be keeping your documents and your spreadsheets. You can also make links to institutional stores where you may be keeping your big data, your sequencing data, or your imaging data if you're involved in life sciences research. We also have integrations with all sorts of tools, both science-specific tools and generic tools. So, for example, with Slack and Microsoft Teams, which are increasingly used as vehicles for communication, with things like GitHub, with Protocols.io, which is, I think, also probably going to be adopted as part of the Harvard Data Commons, which is an open source protocol sharing website or utility, which is becoming very popular. And the list is always growing as well. And plus we have an API so you can build things on top of RSpace yourself. And then finally, at the other end of the spectrum, you can see the Dataverse bubble, I think. So we've integrated RSpace with Dataverse and a couple of other repositories so that it's possible when you're finished with the active part of your search, you need to deposit your data into a repository to make it public. You can do that very seamlessly through RSpace. So this is our story, if you will, and I'm just going to put up again the slide that Merce just showed about the Harvard Data Commons. I think you can see with that as background why this RSpace fits in very well with the notion of being part of a data commons and being interoperable with a whole suite of tools. And I think it also comes back to some of the things that Scott was saying this morning about NERC. The idea is not that scientists they don't just want one tool, they want to be using a whole suite of tools. And for those to be effective, they need to be interoperable. So just looking at the list here, RSpace is already integrated with Dataverse, integrated with Protocols.io. We are going to have an integration with Jupyter Notebooks, for example. So I think this is a core aspect of the data commons which fits in very well with our kind of design approach and our philosophy. So we are also going to be working with Scott and others in the coming year on putting RSpace and Dataverse up as pilots on NERC. And some of the things that we'll be looking to do in conjunction with that are the integration with R and Python notebooks, as I mentioned. And this is actually this is a really practical thing, because if you look at the life sciences, there's a huge divide between the computational side, bioinformaticians on the one hand, who create models, and the wet lab people, which is the long tail of life scientists, which are really users of RSpace. And they might want to cooperate together, but oftentimes cooperation isn't as good as it should be. And there are many reasons for that, cultural, et cetera. But one of the reasons is because they use different tools. So the computationists all use Jupyter Notebooks, and the wet lab people all use things like RSpace. And unfortunately, never the twain shall meet, or often it's the case that they don't meet. So through the integration, we're going to provide a platform that will help in some ways to bridge the gap between those two communities, and that's really an important thing. We are also going to be looking for developing ways of even more enhanced synergies with other tools that are deployed on NERC, Dataverse being a prime example. And something else which is, I think fits in nicely with the NERC model is this multi-campus collaborations. Unfortunately, at the moment, when we deploy RSpace at Harvard, it's not necessarily seamless for collaborators from outside Harvard to access the Harvard RSpace, and likewise if it's the Edinburgh RSpace or the Wisconsin RSpace, whatever it is. And it's possible, but it takes some work. So when it's deployed on NERC, that will provide a very seamless environment for researchers from different universities all to access RSpace. So we're looking forward very much to the pilot, and also looking forward to helping to kick off the Harvard Data Commons. Thank you.
And next we'll have John Goodhue talking about the Open Storage Network. So continuing the theme of various ways of storing your science data. Because unlike us CS people, some people don't throw it all away.
So I'm going to talk about the Open Storage Network. This is a little bit further down the stack from Dataverse and RSpace, but an important part of the mix. So I'll come back to this later, but you can think of the Open Storage Network as a national resource for sharing active open science data with the interesting characteristic that it is distributed infrastructure as opposed to one giant store in one giant place, and also governed in a distributed way. So not one single entity is operating it. So it's maybe closer to the internet than a big Ceph storage stack. If you think about the motivation for this, then you've heard this all before. The godfather of the OSN is Alex Zalay. He's an astrophysicist, also a computer guy. He and Jim Gray wrote the Sloan Digital Archive a while back. But he was noticing, there are actually several Moore's Law effects going on this slide. He was noticing that the photo arrays on the backsides of telescopes were growing at Moore's Law rates, and we're soon about to overwhelm the world. You see the same thing going on in sequencing. You see it going on in brain imaging. At the LHC, Peter said that scientists never throw data away. In order to keep the data down to terabytes a day, the LHC actually throws away all but 1 in 10 million events. They measure their event streams in femtobarns, which you can look up on Wikipedia. It's a really big number. So we are being deluged by data from many different sources. And we're in an interesting place. This is a comment about, and particularly the NSF science ecosystem, but I think it's maybe true in other places as well. For a long time, we've been working on computation, right? Ever since John von Neumann kidnapped the ENIAC and took it to Los Alamos. Networking, there are hundreds of universities now networked at very high speeds. It's actually pretty straightforward to get maybe 8, 9, 10 gigabits per second of data from one place to another. It's quite extraordinary. Storage, on the other hand, is largely balkanized, mostly on-campus storage arrays. The good thing about standards in storage is there are many to choose from, right? But needs a little bit of unification. So that's where we're trying to head. Again, what we're doing is national resource for sharing open scientific data in a way that the governance and operation is distributed as opposed to concentrated in one place. We're doing a pilot right now with 6 sites. A couple of them were founded a long time ago by the Schmidt Foundation. The next wave of sites were funded by the NSF. And you can just see on the map where they are. Part of the point of this was to spread them far enough across the country that you couldn't cheat, right? This really had to be a distributed kind of infrastructure. If I go forward rather than back, just one example. This is actually working with a project that our connection is Chris Hill at MIT. He may still be in the audience. But the idea here is we are, the geoscience community is now capable of generating simulated synthetic data that's pretty close to the real thing for really interesting sizes of ocean. So when you model the Straits of Malacca now, you can generate data that looks statistically a lot like the real Straits of Malacca, which gives you an enormous amount of, an enormous amount of flexibility in looking at different kinds of oceanographic events. The results from these simulations are massive from a data point of view, so sharing them is quite challenging. This shows Chris's computer engaging, engaging one, where he does these simulations, and movement of data between the Northeast Storage Exchange, the MGHPCC node on the OSN, and also exchanging data with the Scripps Institute out near SDSC, where there's another node. So S3 from engaging one to the MGHPCC node. We can drop it down using Globus to the Northeast Storage Exchange, but we can then also transfer it quickly and efficiently across the country, again at many gigabits per second, headed down to Scripps. And I think the principal point of this is it's mostly invisible and mostly fast, so you don't have to worry from a science point of view about where your data is and where you want to get it to. Just to give you a sense for some of the other folks that are dropping data onto the open storage network today, critical zone observatories, enormous amounts of data about kind of the physical and chemical properties of the surface of the Earth. Pangeo, which is not on the list, is a very large climate database. There are machine learning databases that are on their way in, telescopes, and so forth. So there's a wide variety of projects where when you come to them, very often their data is bottled up, right, in their institutional repositories. If you're a large institution, that's less of an issue because you can kind of afford the bandwidth and the management. But if you're a mid-size or a small institution or a distributed project, it's a lot tougher to get the data out into the world in a fast and convenient way. Getting to data sets stored in the OSN is really a multifaceted affair. I think what we found is that the emergence of S3 as kind of a base standard gives people something to hook up to that makes it easy for you to either just do raw S3, and that's what at least several of the initial folks are doing, but you can also overlay it on it things like rclone, iRods from RENCI, Globus, Clouder, CyberDuck, the list goes on and on. And we've had conversations with some folks in this room as well about experimental overlays that do, for example, better ways of unifying the namespace or just moving data or caching data. So it's not only a platform delivering scientific data, but it's open and flexible enough to try some experiments as well. How we deploy, we didn't read Hugh's memo about how it's impossible to deploy systems, so we went ahead and did it. I'll say that the way we did it was we locked Jim Colbert up in his coding cage, fed him steaks for a couple of weeks, and emerged with something that, if you look back down the mountain of where we've come, as opposed to up the mountain to the places that we need to go for management of large systems, it's actually pretty amazing, right? So you start with your Ansible scripts locked away in your GitHub repository. There's a command center, a provisioning node, right, that grabs them. And when you want to stand up a new pod, they link up, provision the monitor nodes, provision the data nodes. So I should have mentioned these are all, multi-petabyte Ceph appliances, thanks to Ceph Ansible and that crew. And it's I'm being deliberately glib here, but at some level, you press the button and you go. We've tested this by burning down the software and seeing how it goes, and mainly the startup time is how long it takes to spin up the disks. The other component to this is monitoring. So we've got monitoring nodes in I think 3 places, actually 2 places at either end of the country. Those are watching, for events, both logging, doing the normal things that you do. But when you publish, so at Harvard, when you publish, you go to you publish an event, it goes to a Slack channel inside of the Harvard Research Computing Group. In our case, the events go to a Slack channel that is embedded in maybe 6 or 7 different research computing groups with a protocol for figuring out how to respond in reasonable time. So again, I'm being deliberately glib here. There's a lot more to do, but it's remarkable what you can do with a cooperative effort, distributed operations and distributed development with the tools that the open source community has allowed us to bring to bear. So just one more thought. I might even be earlier. Somebody's waving a sign at me. Active data sets are welcome within reason. We're loading the network up now. And new sites are welcome also. We have a recipe for dropping in a pod. It may be at some point it's more of a protocol-based thing for existing equipment, but right now we're dropping appliances and would love to have you join the team.
And last, we have,
Not last.
no, not
If you
last,
want.
there's one more after. Okay, Paul Ruth is going to be talking about Fabric? Yes, Fabric, what is it? So we will know in mere seconds.
You'll know the 10-minute version. So my name is Paul Ruth. I'm from UNC Chapel Hill. I work at a research institute called RENCI that has been mentioned quite a few times today. And I'm here today to talk about our new programmable core network testbed that will span the nation coming soon. NSF just gave us $20 million to build this last October. So what I'm talking about today is not yet built, but it hopefully will be soon. And we're looking to get feedback from everyone about how to build it and what you want to see in it. So for starters, this is the team that we're working with. So Ilya Baldin at RENCI is our fearless leader and the PI of the project. Anita Nikolic is second in charge. I'm going to skip several things in this talk in order to go a little bit faster so I can get through most of the things I want to talk about. But there's a bunch of other people on the project. These are just the leadership team. There's even many, many, many more groups that are involved. So the motivation behind this, keep in mind this is a programmable core networking testbed that's going to span the country and connect all your clouds and all your facilities. And the motivation behind this is that the internet has existed for a while. It was designed decades ago. There was certain things, certain limitations that they had, constraints they had when they were designing it, and it's showing its age a little bit. If we had some of the devices and capabilities that we had today, maybe we would have made slightly different choices back then. But since we have TCP/IP and we have routers and we have the systems set up the way they are, we pretty much have no choice. There's the narrow waist of the stack, and we have for years been designing all of our software around this. But this testbed will allow us to do some experiments to see if there are other possibilities out there and let people be a little bit more creative. So what's changed? Well, compute and storage is a lot cheaper than it used to be. We can think about putting it everywhere in the network, for example, and it's not really going to cost that much compared to everything else. We have all these really cool network programmability tools like OpenFlow and P4 and DPDK and all of these other things, and probably more will come along the way. These didn't exist back then. Now that we have these software-defined networking capabilities, put them in the core of the network, let experimenters use them, see what they can come up with. We had machine learning and AI, which is just changing everything in all different ways. And really our applications are very different. So like, everyone has a phone in their pocket that'll soon be 5G. There's IoT devices everywhere. No application is a standalone application anymore. There's always some sort of cloud piece. So the networks are really just part of the applications these days. They're not these end-to-end things that we used to think about it. So we have opportunities to change some things. This is just a test bed that will allow people to experiment with it. We have no horse in the race to see what technologies win. This is just a test bed to let people try to do things that they can't do with the internet as it exists today. So what are we actually going to build? Well, there's two pieces to this. There's the core of the network, which is in this map here, and there's going to be the edge of our network, which I'll show in a little bit. In this picture, there's 9 sites around the country that we're going to actually get hardware and put it in there. These are the core of this network is going to sit on top of ESNet 6 footprint, which is ESNet 6 is currently being built right now, so we're sort of dependent on their rollout before we can roll out. And at each of these sites, we're going to have, you can think of it as like a rack of networking gear, like P4 switches and programmable things and storage and compute and connections. Between them, we're going to ride on top of ESNet 6 again, and we're going to have dedicated optical links where we own the lambdas on the optical links. The blue links up there will be 100 gigabit connections that we own the whole 100 gigabit. The yellow supercore is going to be a terabit link, which we own the whole terabit. Now, of course, probably right away, no one's going to use the whole terabit, but since we have a terabit, that means I can give you 100 gigabit, and you 100 gigabit, and you 100 gigabit, and you won't get in each other's way, right? So that's the idea behind that. Also interesting in this picture is we don't really have any edge compute in our system, and that's by design. So instead of us providing the edge for you, we're just going to connect to all the real things. So for example, we're going to have another site in the MGHPCC. We'll have it in all of these different NSF cloud sites and high-performance computing centers and various regional networks and all of this all around. And you will be able to then connect your real facilities into this network and design topologies that go across it and possibly even connect it into the public clouds via internet too. So this is the core of our network. There's actually 4 more core sites that we haven't decided where we're going to put them, so they're not on the map yet. 13 of them total. There will be 16 more sites that will look just like this, except they'll be in different regionals. Like, for example, the one that's in MGHPCC, or will be in MGHPCC, will be one of the 16. We're going to do our best to connect all of the other 16 sites with dedicated optical layer 1 connections at 100 gig if possible. We do realize that not all 16 of those will be amenable to that, so we're going to do whatever we can to get the best connections we can. The 16 sites, these are our other partners that are on this project. There's lots of them. UMass Amherst is the group that signed the letter for us, so that's why their logo's here, not MGHPCC. All of these places will have some affiliation with us for some connectivity or some sites, or maybe they have applications. They're all getting paid money out of this somehow. So that's what these are. And these would be the edge of our network. So people that have maybe seen this presentation before probably haven't seen this slide. We're actually making progress towards designing things now. So this is where the concept behind the fabric core will look like. So in this picture, there's sort of 2 main colors. The gray color is the things that we will run. The administrators will run this. The yellow, tan colored ones are the ones that the users will be allocated. The users can create these resources. So if you see here, we got this switch down here, the data plane switch at the bottom. It's got, in this picture, there's 4 links that go outside. You can kind of imagine those as being 100 gig links going in some degree to other fabric nodes. We have maybe a P4 switch or maybe several P4 switches. P4 switches can only be controlled by one group, so that if we have a P4 switch and we allocate it to you, you will get full control over that. Over here we have nodes that are just regular compute nodes, and in those nodes they'll have all sorts of programmable things, all the things you want, all the things we've talked about. I won't go into it so we can save some time. And we will use this data plane switch here as basically a patch panel to take ports on all these different pieces and plug them into ports on all the different pieces. So you can get a P4 switch connected to your FPGA as a bump in the wire, connected to a circuit that goes at 100 gig across the country to some other node that looks basically the same, right? That's kind of what we're doing. Or you can have it go out with our data plane switch and connect to some big facility inside, for example, the MGHPCC. And that's kind of what we're going for here. So an example might be like this. So we have something you might deploy would have a bunch of sites, maybe a P4 switch in Texas and some set of smart NICs in the middle of the country, come to the West Coast through a bump in the wire site that connects to some external resource in California. And you can design this. These are all dedicated to you. You get bare metal access to all of it, connect it up to your real things, run your experiment. That's the idea. We get this. We have to make sure we talk about this. So there's a lot of stuff going on here. The real takeaway here is this is a programmable core network. What we want you to do with this is to do things you can't do with the internet. So we want you to program the core, put state in the core, things like that. What we don't want you to do is say, I got a bunch of genomics data on the West Coast and I'd like to get it to the East Coast. That's for someone else to do, Internet 2 or something like that. We can work with you to make that happen, but that's not what we're here for. We're also not for production traffic. We're more for experiments. But we do want to serve as an incubator to take your experiment to like a semi-production state so that you can then like test it out with real traffic, and then we can go to Internet 2 or someone like that and get you a real place to deploy it. So we want to incubate you. The timeline, so we're still in year 1. We got funded in October. We're still planning. Starting in year 2, we're going to be deploying real devices, a small subset. And then years 3 and 4, we're going to deploy the rest of it. Probably by next summer, somewhere near the middle of year 2, we'll want to get real users on it for a small pared down version of the topology, but it'll exist. So we invite you to come try to use it. If you want to get involved, we have a website. You can go here, whatisfabric.net. Click on the Get Involved button, and there's a little form you can fill out. You just be on our mailing list. We'll tell you about workshops that we'll invite you to and things like that. And, whoops, go to the next slide. It doesn't want to. There it is, okay. And NSF paid for this, so thank them too.
Okay, and our last talk is going to be Julia Kreger, and what is ironic and where is it going?
Okay, this is. Okay, does that work for you?
Thank you. Hi, everyone. Perhaps I should stand closer to the microphone. Hi, everyone. My name is Julia Kreger, and this talk is Where is Ironic and Where is it Going? So a little background. Ironic is the bare metal as a service project for OpenStack. It was first released nearly 6 years ago, which seems like an age of time that I can't even think of. 5 years ago, it actually became part of OpenStack, and since it actually started, 808 people have contributed from 96 distinct organizations. In just our last release cycle, 103 people from 36 different organizations submitted patches. Now, one of the things I do like to talk about briefly is the adoption of Ironic and where it is in the universe, because you can't really know where you're going until you know where you are. So in OpenStack, multiple projects have integrated and leveraged Ironic for various deployment needs, and not just deployment of installation, but also deployment of instances. These projects are the Nova project, OOO, and Kala. All of these problems solve specific problems and use cases in the Ironic or OpenStack community. But the thing to take away from this is that the user base of Ironic continues to grow. A new project called MetalCube recently started. I guess it was actually about a year ago that started. And the intent is to provide a Kubernetes CRD to drive Ironic. Where this is going is MetalCube and also additional OpenStack projects are beginning to use Ironic, and now we're seeing Airship, which is another OpenStack community or OpenStack Foundation community project, and OpenShift also taking use of Ironic through Metal Cubed. Awesome. So a little bit about the velocity of the project so people are aware. What we've seen is both a decline and an increase in the number of commits. And we've also seen some operator commits jump in and also kind of decrease as various problems were solved. But we've also seen a decline in committers. And what this is this tends to be drive-by commits. People seeing a minor problem and going, I need to get this fixed, or someone doing a one-word minor tiny little change across 100 repos. So we can kind of see when we look at the amount of code that's been added and deleted to the project, that it's also kind of staying fairly stable. It's evolving as needed, and really it's not changing too dramatically. Right now we're kind of in a feature additions mode. But the key takeaway is that Ironic is a stable platform, and when we talk about clusters, hundreds of machines that it manages are fairly common. When we start talking about the hyperscalers of the world, people are running 4,000, 10,000 machines in Ironic in a single deployment. I know of one cluster that's at least 150,000 machines, which is kind of mind-boggling when you think of the number of cores that can be in those 150,000 machines. So, kind of explain where things are going. This train was our last release, and we added a number of new features, one being software RAID support, another being multicast DNS support so that Ironic services can find each other on a network. You don't necessarily need additional configuration. We also became the authoritative state for power information, which was kind of a big change for the compute universe. We also introduced this concept of deploy steps, which is allowing operators to better articulate exactly how to reach their desired end state. And also, we've seen more use of Redfish. Specifically, Dell has added interfaces to support Redfish hardware through their what we call hardware type. Since then, we've started working on Redfish Virtual Media, which is another feature, to allow operators to deploy machines using virtual media and not pixie booting. Redfish is a DMTF standard, which is Distributed Management Task Force that is defining an API surface to control hardware. If you've heard of Swordfish, that's another project that is in their community, and the whole idea is to provide a common vendor-neutral API framework to kind of replace things like IPMI. Many reasons, but we shouldn't go there now. One of the other features we added was the ability to collect sensor data from Redfish, specifically so you can provide that to your instrumentation tooling and expose that to your users. We also had a couple more features to collect additional information, retries, little things to make things easier for operators, so they didn't have to define the same data on machine after machine after machine. Now there's the current development cycle. That Redfish iDRAG virtual media support is now a thing as well. So we now have a framework for multiple vendors supporting virtual media-based booting with Redfish. We also now support the automatic allocation of serial port consoles. This wasn't a thing for years. It used to be a manual thing. Who knows why? We also expanded our software RAID support. And we may even see additional support to constrain the actual selection of disks before the end of our development cycle. We're also seeing lots of work into multi-tenancy, which is very important for the mass open cloud. And with this is also coming the support to do privilege delegation to users. While not turned on by default, the concept is that certain users will be able to actually have additional privileges. So if I was deployed via a virtual machine, I could potentially go to Ironic directly and say, please turn my machine off. CERN has also graciously added support for a logic called retirement, which allows an operator to say, I don't want to reprovision this machine. I want to shut it down at the end of its life cycle, but it may stay beyond for months for all we know, because people actually put workloads on machines that can't be turned off immediately. We're also working on security enhancements for edge machine deployments. And what I mean by this is more servers on telephone poles or servers in racks that are buried in the ground, where you want to still deploy them, you still want to be able to perform actions on them, but you don't want to roll a truck. And you still want to do these in secure means without actually having to go touch the machine. We're also working on adding in the ability to control indicator lights on the machines, which seems like a minor thing, but when you're walking through a data center and you have 1,000 machines, it's a little helpful to find the machine that's blinking or be able to turn the light off or on or whatever state you need. One of the things we're also working on in the future is removing the need for DHCP. Turns out that people don't really like DHCP in certain environments. Additionally, with the urging of the scientific community, we've been looking at supporting kexec, which will hopefully reduce that boot time from possibly 30 minutes to 30 seconds. And also, we're looking at supporting persistent agents, and the idea there being, I want to redeploy this machine right now using kexec and reprovision it to another tenant, potentially, or another workload, without actually taking that initial tax of doing this power on self-test. If there are questions, or if you wish to contribute, we can be found on IRC in the #OpenStack-Ironic channel, on irc@freenode.net, and we tend to like people saying good morning.
Okay, thank you, Julia. And I'd like to ask everyone who spoke in this session to come up for a brief question and answer session. What? Okay. Okay, yes, if everyone who's here from the morning session, if you'd like to come up as well. All right, the number of things I want to ask the definition of after that talk. It's quite amazing. Something like that. Okay, so this is where you get to, since we had these rapid fire talks and really didn't have time for questions, we have a few minutes now for that. So who wants to be first? Yes. Yes. If there's I think the mic's on. You could just.
Hi, I'm Phil Durbin. I'm a Dataverse developer. I have a question for John Goodhue. You mentioned Clouder, which is something I've heard about here and there, but I don't really know much about it. Could you tell us a little bit more about what Clouder is?
No.
Oh, okay.
It's a package of software tools for gaining. I'm terrible at talking through this mic. Sorry, gaining access to cloud resources, but the web would be a much better source than me.
Thanks.
So I got questions for all of you, but I'll just start with one. So for the Harvard Data Commons, it seems like is this a gated community? Is there some reason why you're doing like? Is it that I mean it's being stood up on top of NERC and it's being stood up on top of NESI?
Yes.
And is there a reason that we couldn't make this available to the whole community? Although you're obviously going to be focused on features that you understand from Harvard, because there's all these collaborations between the universities as well.
Yeah, so there is no technical reason or even necessarily political reason to make it only part of for the Harvard community. Well, several things. First, we were trying to do some within the institution. We were looking all the challenges that we have now to track where are the published the active data, where are they documenting it in a way that then can be made available later after the studies is finished. And so we were trying to solve how do we address that within the community, but using tools that could expand. I mean, it's still open, using interoperable, new tools that could expand to any community in some way, right? But since we were trying to solve a research data management challenge at Harvard, we were asking for money. We're asking for money at Harvard. So there is I mean, it's not that it means that it has to be only for Harvard researchers, but it is a way to be able to track what happens within our institution. At the end, this is the way we plan to build it. It will depend on permissions. I mean, it could be applied to define the community in a different way, and be the community BU, Harvard, MIT, Northeastern, UMass, for example, and that for some data sets that are shared across, this is the community. So it's completely, the idea is to make it completely extensible. Not only that you could take, some of the idea of that dashboard or that interface to track some of that information, it could be very useful to the administration of one institution, right? And so you might want to have your dashboard view within what data sets are active in that community. So each one has a different view, but are using the same tools.
Yeah, so
I hope that helps. And yeah, if you
so
want
to follow up with Merce, because we're working on this together, is that the reason why it's Harvard is because also we're interfacing with the libraries, and the entirety of the digital repository service that is the Harvard's collection would be a part of that. The whole framework and what we're designing, we're not designing on our own. We'll design it with a number of different partners. So the framework itself would be available for other people to emulate, right? So.
Yeah, but there's a difference of the framework being reproducible. Like Dataverse, you get multiple Dataverses.
Sure.
There's also Harvard Dataverse where a lot of people host their data sets.
Right.
I was wondering if this was one
Yeah.
model or the other, where you're just assuming other people reproduce it, or
No, I
you
mean,
think about building a service that other people, at least regionally, using the same resource can be a part of.
the idea, especially like with the Dataverse front end, and then some other collaborations are happening in that space, is that the front end of the metadata is federated all over.
Good.
And at some point you have to decide who and how you give access to stuff like that. And so this impact group that's doing all sorts of research has cool ways to do that.
We won't build it in a way that it's only usable for Harvard. It could extend that if the data sets are
Okay. That'd be really-
are
sounds very
collaboration
cool.
across. Thanks.
So this is a ironic question. In multiple senses. So I wasn't the guy working on this directly, so I hope I can phrase this question directly, but my group works on, we have an HPC center, and we've also been experimenting with OpenStack for a few years. And it's been, I want to say, a year and a half or more since we last looked, but one thing we were interested in doing with Ironic was basically we have a node that is running normal VMs in OpenStack, and then we also have this HPC side, and we want to say, well, we don't need so many VMs right now. Let's make those nodes that were running VMs bare metal and make them HPC nodes. So spin them up, provision them using Pixie Boot, normal stuff over there. And then, our VM side needs more stuff, so let's turn off the jobs over here and put it back in and let it become a normal VM thing. Now, when our team looked at this, with Ironic as of a year and a half or 2 years ago, they couldn't figure out a way to do it. I'm wondering if that's feasible now.
You're basically asking a workflow question and a systems management question, which is not something the community has actually solved in this regard specifically. It's kind of, in a sense, it would be the holy grail, except people also want to be able to track these machines down and be able to service them as needed. So it ends up in this weird situation of, have I architected something, or did it just magically deploy in a way that's didn't want it or can't actually operate it?
Okay.
So I would say if you develop tooling to do that, many people will be interested, but many people won't be able to leverage that tooling at the same time.
Sure. Thanks.
I should just add one thing to that, which is that I believe the scenario you just described is precisely the goal of the Elastic Secure Infrastructure project. which has been responsible for contributing a lot of the multi-tenant features to Ironic. That's something that my folks work on. We do hope to have, within 6 months or a year, a tool that will let you quickly either power down a host or maybe even kexec it for a new user with a different boot volume, which should let you do exactly what you said, move workloads from HPC to cloud and back very easily. There is also a nasty little network provisioning bugbear that we haven't quite solved yet, but it's another thing that's in the works. Moments away. In fact, it should be happening now. If I shut up, we could start the birds of a feather. I have one more question for Julia since I'm standing here. Speaking of ESI, we were talking about a year ago, I think, about boot from volume support in Ironic, and I wonder if that's on the roadmap or if it's already done or something you're still thinking about.
It was implemented two and a half years ago, I think.
Huh. How did I miss that? I think I was specifically, at the time I was specifically thinking about booting directly from CephRBD, and that was trickier, if I recall.
That is a problem because of no bootloader or not RAM disk scripting actually supporting a standardized set of kernel arguments to actually articulate what volume to connect to and the authentication issues with CephRDB. I believe someone actually implemented support to actually use the iSCSI gateway support in the Cinder driver.
But Cinder volume has been okay for a while.
Cinder volume that's iSCSI backed.
Yeah, okay. Thanks.
If there's time for one more, I'm curious about Kubernetes and if it interacts with any of your, if it has anything to do with any of your projects.
Well, I know, yeah. At least from my project standpoint, people are using Ironic to deploy Kubernetes clusters, but it's all mechanics at that point.
Oh, well, if you have one more. Okay, there's nobody here representing Open Fabrics, is there? None of you. Ah. No, the talk this morning about Open Fabrics. Oh, Open. Oh, well, if you can answer the question, because the question was going to be about interconnects. Okay, right. I have one for Julia then. When you said kexec, you must be using a Linux BIOS. Which one?
Not yet.
Okay, so how do you kexec?
We run a persistent agent, or we kexec from the running RAM disk.
So you keep Linux round in the RAM disk, and then that kexecs. Okay.
So I asked a few people that sort of were part of the core organizing to get up and say a few closing remarks. But while they're getting up there, I guess I have one more question. So for the Fabric stuff, I know, but I get to cheat. For the Fabric stuff, it seemed like it'd be valuable even internal to the data center. Like, can I set up some open cloud testbed nodes and then actually use to multiple ports on this Fabric connector you're giving us?
Absolutely. Yeah, that's
Okay,
definitely something that can happen.